So we do have a few minutes here. I will ask you to unmute, and then John as well. Okay. So I guess the question, let me start with the questions here then. The first one would be, you've talked about the information universe several times, and I'd just like to clarify for the audience. So you told me the other day that this is different than Bohm's holographic universe. The information universe is kind of another, like a string brain type dimension that can basically controls the rules that drive the material universe, right? Is that the way you're describing it?
John, you responded to, so I'm going to let you speak. Is he,
I didn't hear all that.
I'm just wondering.
Sorry,
I'm sorry. Is there kind of a layman's description of the information universe? I'm trying to connect this back to things that are a little bit more tangible for kind of the average person.
Well, yeah, I think that Dirk Meyer had it in his paper. Basically, it's just a whole bunch of threads that are regulating different 3D elements, and they're all communicating and sharing their rule learning, and they essentially he called them blinks. Time goes along in blinks, which would be time is also discrete. So you have you during the blink there's no time, and you fix it, you regulate everything, and then they synchronize time up throughout the universe, and then they go have another blink, and then I thought that was a pretty simple model. That's what my little model does.
Oh, okay. Well, and then from a propulsion aspect of this, if I could ask a little bit about that also, have you found any insights? And this might go to Amar, because again, okay. Amar, I know you've worked with Searle and Bearden. Have you found any insights that might help from the propulsion aspect?
Absolutely. Well, yeah, I don't want to. Here's what we actually had a talk with John Fry. Fry Electronics. It was in 2017 because he came down. He was curious about what we were doing too, and so he gets into some deep philosophical discussions with us. It was at Cal State Dominguez Hills, and in the math department. I can document that. I think so, at least. I hope so. But no, we were there, and anyway, frequently what happens and when these discussions come up, especially these extreme topics, is that, well, heck, where does this energy come from? I mean, we talk about this, and I was struggling with that too. And I said, Richard Feynman said, I like Feynman and I like the way he thinks. And he said, look, I don't even know what energy is. And he's right. We don't know what it is. We know how it works, but we don't know what it is. We don't know what force is. Well, then I started thinking, I said, Tom, John Searle, and I, when we would talk, one thing Tom would keep talking about is this energy that's trying to hemorrhage into our 3 space. He would say that this is there's a 4-dimensional energy that's trying to hemorrhage into our 3 space, and he'd say that, well, this energy is compressed by c², and I understand what he's getting at. And of course, what he's saying is that time is a very real thing. I mean, I'm talking in terms of Minkowski's ICT. It's a very real thing that it's not an illusion. It's real. Except, and he talks about time polarized photons. Okay, I don't want to get too deep into this because it can get hairy, but that's okay. I want to stay focused on your question. Well, what I was asking myself is, well, maybe as Dr. Clymer, as John said earlier, that, and I really resonate with this, and Dirk's talking about this too. Smolin gets into it. He says, where's the qualia? Qualia, qualia. How do we fit into all this in this qualia? Because it seems, and there are papers published on this, where rigorous papers, They're saying that when you try to get into the world of energy, even when you start studying certain subtle things in energy, you run into problems in mathematics. They call them inconsistencies. Okay, and a fellow mathematician, well, I mean, a fellow mathematician of Einstein. Well, let me frame it again. Let me rephrase this. And a mathematician who was well involved, very much involved with Albert Einstein, and I think Hilbert, maybe Hilbert. Anyway, he was the Kurt Gödel had put together a theorem. He was able to show that, look, mathematics itself is inconsistent in certain cases. Well, it turns out now there are some papers that are being published. They're saying, look, we can't even. It seems that there is a lot of this going on even in the field of energy itself. Just the study of energy in itself, there are things in it that are intractable to the extent where it leads into these paradoxes. Now, what that's saying is that it's almost as if it's axiomatic in the sense that it was already there. How it got there, we have no idea. What is it? We have no idea. It's as if there's, in other words, you can't wrap it around with mathematics. It's almost as if math takes a back seat when it comes to this stuff. So what I'm trying to lead up to is this, is that it could very well be that the information universe is what is basically giving is as Dr. Clymer and I discussed this, is that it has to test itself out. So it has to find some kind of an optimal way of going about doing it to see if certain things work. In order to test it out, it has to have a place to test. So it creates an exhaust, if you will. That's you can call it space-time. And in this exhaust, the part which is where the information universe and the material universe are actually adjoining is this hemorrhage that that Tom Bearden is talking about, this structured energy in the time ICT. But we don't observe it because it's happening at a very, very fast pace, high speed. And also, what we are detecting is the stuff that we can observe, not the things that we are, not how it's interacting. We don't know how to since we don't observe it, we don't see its we can see its effects in things that are far from thermodynamic equilibrium. But that is if we are willing to actually pay a close attention to it. For example, us being human beings, we are ourselves far from equilibrium. And what our brain is capable of doing, our heart, everything, what we're doing as a whole, as a system, is so complex that it appears to be being regulated by this IU. But how is it doing it? It could be what is adjoining it is this structured information in the time ICT. And so so to get back to the propulsion part, is that what we're trying to see is, considering that we may not be able to wrap the math around some of this stuff because it may be that it's just there, then the question is, how do we tap into it and use the information universe? In other words, do the precursor engineering in the information universe to create the effects here. So this is kind of getting into the realm of, we're talking about an emergent phenomena. And it's this is sort of at the crossroads of at the edge of knowledge right now. So it almost sounds fantastic, but it certainly solves some of our major problems that we're having right now. And anyway, I'll leave it at that. I don't know if that answers part of your question. Go ahead.
Right. Let me add something. The Dirk Meyer papers, most of them have to do with how the human brain interacts with the information universe. And this goes along with what I call the quantum brain theory. And those of us that are familiar with neural networks know there's no hell that our human brain could do what it does based on just the neural network that's up there. That the idea is that the neural network is actually a function of quantum states and probably connected to the information universe. and makes use of the information universe and in some way to greatly expand the capability of the brain, you know, to be entertain a vast, you know, vastly increased number of behaviors than would be possible with just the neural network that's there. Neural networks are very brittle, so this thing's got to be changing as a function of quantum state. And anyway, Jerk's got a paper out where he talks about that. Several, actually. It's quite compelling, actually, the idea. It's like the information universe is speaking to us all the time. You know, we just listen.
Yeah.
Maybe that's where a lot of insights come from. You know,
Well,
I know that sounds crazy, but I think it's true.
Maybe jump in on that. Just a quick thing.
sure. You know, but before you jump in though, let me ask, because I mean, we have 27 people in the conference, 25 other folks. There's Will. So after you go, Will Reichen had a question. So yeah, go for it, Amir.
Yeah, you know, there's another thing. In fact, I just recommended John a book, and he just ordered it. I was going back and studying Minkowski's he gave a topic. He gave a talk. I think it was in 1908 at Cologne, Germany, and Minkowski gave a talk on his map that was, of course, building on the Minkowski framework geometry. And I gotta tell you, what he was really saying, I think, was I don't know how to say this in the way I want to say it, but it seems that as if it may have been something may have been overlooked, that we need to go back and look at listen to what he, read his actual presentation, listen to what he said. It seems that because of his mathematical insight, as I understand it, Einstein did not quite catch it the first time around, and then he started realizing he had a need for it when he got to GR. But when I read this material on Minkowski, I think it's from Minkowski Research Institute, I was able to see that there was a lot of things that Minkowski did not get credit for, and he should have been given credit. And I think it also turns out that he may have been misunderstood, because he was tending to be more in the mathematical realm. And I'll tell you, let me get to the punchline. Let me get to the key points behind it. What he's really saying is that your space-time and my space-time are personal. And I recall another gentleman saying something like that. I can't quote it, but I do recall him saying personal, was Kip Thorne at Caltech, that your space-time and my space-time are personal. So your world line and my world line are different. So if you look at that as a system science, as a brain, the brain has all kinds of things going on all the time, dynamically. So it has its own space-time world lines. So we really go back and look at the physics that Minkowski was trying to get across, and really understand the way he was presenting it. I think we'd see a lot of things that perhaps might help shed more light in special relativity and the general relativity that may have been perhaps missed. I'm trying to say this in a nice way, because I have no disrespect for anybody. Try to like this as much as I can about this.
Okay, well, let me do this. Thank you. Let me go to Will Reichen, and again, I should apologize. We're running low on time, so I want to try and get Will in. Will, sir.
Okay. Okay. So, as someone who is a computer scientist and who has spent many years in evolutionary systems and neural networks, I feel that your data sets are too small. It's very difficult to know which neural network you're using, as you don't identify the category. And each neural network method also has different ways of handling the in data sets. So, and then the other thing I would like to say is that evolutionary neural networks are even more difficult than standard neural networks, neither one even approaching the level of the human brain. So my question on that is, do you plan to expand your data set and in order to get more finer resolution for what you've already done? And then I would like to make a statement, and that is that because you brought up the photon. If you were standing in the blackest, darkest room in the universe, and you had the right type of vision, then a single photon has enough energy to light up the darkest room in the universe. So bright that you can make out all the features in the room as if it's broad daylight. So I'll just make that statement because that place does exist. I just can't see anything about it.
Okay, and so I think Will's question. Thank you, Will. I think his question was: are you looking at expanding the data set to be able to get finer resolution with the neural network results?
Absolutely.
Well, can I answer that?
Sure, sure.
Then what Amar can answer. Okay. Well, what I'm doing is when we generate a training set, we would generate all possible combinations of our frequencies, energy levels, and waveform. Well, you know, it might be 100,000 different ones, and when we run it through the neural network, well, basically we're trying to learn the mapping to go from the n-dimensional space to the feature space, which is embedded in it. It's a closed manifold that's embedded in it. So that's all the neural network is doing. It's just learning that mapping. And the way you know you got the right mapping is when the rules work. It's very simple, really.
Well, I understand.
And
The training,
as big as you think it is.
Oh, okay. Oh, I may have thrown Will off. I was.
I'm sorry. I didn't realize that sorry, I made a mistake. I didn't realize I actually had the mic on.
Oh, okay. Okay. Yeah. Well, so I think. Oh, yeah, and I was responding in chat to Will's thing.
I mean, that can be as large as.
You need me to jump?
Okay, well, Will is asking about the size of the training set. And he's right. It can't be infinite. You're going to have to set boundaries on, you know, what disturbances you're going to be experimenting with. And you can make that as big or small as you want. And probably end up doing it many different until you find the right I would call space, training space, you know. But then all you're doing is mapping that training space into the feature space using an evolutionary neural network, which means that evolutionary algorithms are being used to do the mapping. So it just keeps, you know, generating population after population until it produces what you want. So, and all it's doing. It's just mapping from the raw data into the feature space. The feature space is what does the discrimination. So the raw data is a lot more data that tells you anything. So you map that into the feature space, which basically does the discrimination. That's all there is to it. And we use evolutionary algorithms to do the optimization. So,
I could jump in.
yeah.
So,
Yeah.
yeah, I can work. I can make it as precise and accurate as required by the, depending on what we need to do. And of course, this thing is autonomous. It continues to explore. It's unsupervised. It continues to explore on its own within that precision and accuracy. Also, it's in a deterministic. It's in a deterministic framework. In other words, it's learning just like John's program is learning, but it does not rely on any a priori. It doesn't care about a priori. A priori meaning that there's some kind of a distribution beforehand. No, it could be anything. It's going to try to learn, and it's going to try to find out what it is. In effect, it's like getting a. I don't like analogies, but it's like getting an image of a example, and you're trying to get this. If you put a penny under a piece of paper and you scratch it, if you scratch it coarsely, you're going to get certain things. If you scratch it finer, you're going to get more things. But in this case, we don't even know what we're looking at. So what I'm doing is I'm finding out what these things are, and they're dynamic. So this is hard to describe, and even analogies are not that good. But it's that kind of a thing.
Could I interject something here?
Well,
I think there might be a confusion between a large feature space involving a very large number of different disturbances versus what Amar does, where he takes data from one disturbance and tries to extract the information that discriminates that one. So it's two different things going on, and both of them are critical to solving the problem.
yeah.
So,
guys-
so I guess really what I wanted to
That
ask
makes sense.
is how different are you then from NMR? I mean, NMR does almost the same thing, doesn't it?
Oh. No, because go ahead. Who's? Do you want me to?
Like I said, I'm trying, but I have to take what Amar gives me as the truth about that disturbance, individual disturbance. He's going to tell me, he's going to give me information that will uniquely discriminate that disturbance. And then that goes into the database with all the other disturbances. And then I try to cluster and classify all those disturbances and map it into a feature space.
Yeah.
John
So
saw.
guys, let me actually, I think we probably need to move on. So let me do this. Let me mute you both out. We could probably come back to this in Q&A if you're both with us still then, but let me do a mute all. Okay. And let me see, I'm gonna go to gallery view. And again, everyone, please give Amar and John an enormous hand. Thank you very much.